during the jump up, wave, or something if you have a question and want further information, and Drew will do that. So let me turn it over to Drew and get going.
Thank you. Yes. Thank you all for having me tonight. I'm excited to tell you about LIGO, its design and destiny. If you don't know what LIGO is, hopefully by the end of the presentation you will, and you'll also know why it has been contributing to astronomy and will continue to do so for many years to come. First of all, who am I? I have been married to my high school sweetheart for 17 years. We have 2 kids, my wife, Lisa, my daughter, Moriah, and my son, Samuel. I'm a Christian, and I enjoy exploring God's creation through physics and astronomy and many other fields of science. Things I enjoy doing include cooking, playing board games with friends and family, traveling, reading. One of my favorite cooking experiences was at Caltech when I was taking a cooking class. I got to cook for Stephen Hawking. One of my favorite places that I visited is in Bern, Switzerland. I was able to visit Albert Einstein's apartment where he lived and worked. And the thing I enjoy reading the most is science articles and textbooks. So as you can tell, I'm a pretty big nerd and I'm proud of it. One of the biggest ways that I have shown this is by convincing my wife to name our first dog Maxwell's equation. This was after I took a general relativity course and learned that Maxwell's equations that govern electromagnetism can be formed in a single equation. And that really enthralled me. So I had to name my dog Maxwell's equation. Not only do I enjoy science, but I've also been able to turn it into a career, which I'm really enjoying as well. My background is in math and physics. I have a math and physics major from the University of Wisconsin-Madison, and that's where I first started doing research. I started doing research studying silicon germanium quantum dots, but then in graduate school, switched to general relativity. I have a PhD in physics from Caltech. I studied gravitational wave physics and data analysis while I was there. I worked under Professor Alan Weinstein there within the LIGO lab, and this is a picture of me with Alan. While I was there, I was also a member of the TAPIR group, which is the Theoretical Astrophysics, Including Relativity group, and got to work with Kip Thorne. After I graduated Caltech, I was then a postdoctoral scholar for a little bit at Caltech before moving on to become a senior scientist at the Albert Einstein Institute in Hanover, Germany. And I spent several years there before I switched careers and went over to industry. For the past 8 years, I've been working in synaptics as an algorithm and firmware systems architect. But this talk is going to be more about LIGO and what it has done, and a little bit more about what I've done with LIGO. When I first started doing general relativity, I was studying the dynamics of orbiting, spinning black holes, and how, as they orbit each other, the black holes will actually bob up and down. I worked with Kip Thorne on that, and together we have a paper with a few other people. I also studied numerical relativity and enjoyed doing numerical relativity simulations. These are where you take the equations of general relativity, code them up in your computer, and then run simulations for things like black holes colliding or gravitational waves focusing and forming a black hole themselves. As a member of the LIGO scientific collaboration, I was able to go to the LIGO detector sites during the S5 observation run. And there I was able to see the detectors operating, as well as be able to contribute to what was going on there. That was something that was very fascinating to me. I loved that. For what I did, how I contributed to LIGO data analysis, I was focused on doing gravitational wave searches from binary neutron stars and binary black holes, searching for gravitational wave signals in the data from LIGO. One of the favorite things that I contributed to was the low latency data analyses where we take LIGO, the data coming from LIGO, as the gravitational wave signals are coming into LIGO, you analyze the data very quickly and then can send an alert out to telescopes saying, there was a signal, a gravitational wave signal from this part of the sky, you should point your telescopes there and hopefully see an electromagnetic counterpart to the gravitational wave signals that LIGO is detecting. The rest of this talk will be focused on these areas. First, I'll give a brief overview of gravitational waves, and I'll talk about what LIGO is. Then I'll talk about how LIGO is contributing to a global network of gravitational wave detectors and why having a network of gravitational wave detectors is important. After that, I'll focus on gravitational wave sources and the detections LIGO has made, as well as looking at what LIGO can contribute to astronomy going forward. So first of all, gravitational waves. Gravitational waves are predicted by general relativity, and they are essentially ripples in the fabric of space-time itself. They're emitted whenever you have accelerating objects, and they will propagate out at the speed of light from those objects. The gravitational waves, as they pass through the Earth or us or any gravitational wave detector, they cause a stretching and squeezing of space-time. And that's the thing that the gravitational wave detectors have been designed to detect. What is LIGO? As Bob said, LIGO stands for the Laser Interferometer Gravitational Wave Observatory. It's a detector, it's actually a pair of detectors, one in Washington, one in Louisiana, that have been built in order to search for gravitational waves. These detectors are essentially interferometers where you have a laser source providing light into the interferometer. The laser gets split at the beam splitter, and then half of it travels down one arm of the detector, half of it travels down the other arm of the detector. At the end of each arm, there's mirrors that bounce the laser light back, and at the beam splitter, when the beams get back to the beam splitter, the photons will either combine constructively or destructively. And there's a photodetector down here that looks for the signals coming out of the interferometer. These detectors are 4 kilometers long. So there's 4 kilometers between the beam splitter and the very end mirror that's bouncing the laser light back. If you look at the Hanford detector in Washington from a plane, this is what you'll see. You see one arm here. This is where the laser source is, as well as the beam splitter. And that laser gets split into 2 beams, each traveling down separate arms, each 4 kilometers long. What a gravitational wave source will do as it comes through the detector is it will squeeze one arm of the detector while stretching the other arm of the detector. As the interferometer's arms are squeezed and stretched, this difference in the arm lengths of the detector will cause a signal to be seen on this photodetector coming out of the LIGO interferometer.
Well,
yes?
could you explain to me what a gravitational wave actually is? Is it a radio wave? What is it detecting? What are we detecting?
So it's not an electromagnetic wave like radio or light.
Okay.
It's a stretching and squeezing of space-time. So if you have a ring of particles that's just floating in free space, as a gravitational wave passes through those particles, the distances between those particles gets moved and they get stretched and squeezed. One direction is squeezed while the other direction is stretched. So it's completely separate from electromagnetism. Yes?
What's to prevent you from detecting seismic events like this?
We do.
That they're gravity waves.
As opposed to gravitational waves. Well, as I'll show in some upcoming slides, you'll see how seismic events would affect the gravitational wave detectors. Okay. These detectors are amazingly sensitive instruments. While I was at one of the LIGO sites during the observation run S5, Delivery trucks that were driving in the parking lot, going over a speed bump, would cause the lasers to get misaligned so that we couldn't run the instruments anymore. We'd have to wait for the lasers to get relocked before we could start collecting data again. Even waves crashing on the shores of Louisiana during storms can cause enough ground motion to make the detectors not be able to be locked. And you have to wait the storms to pass before you're able to run that in the barometer again. These detectors are so sensitive that over a 4-kilometer long distance, they're able to detect changes in the distance of the arms down to 1/10,000th the width of a proton. In terms of astronomical objects, the nearest star is about 4 light years away. If LIGO was able to detect that level of distance change for that star, you'd be able to see that star getting closer by smaller than the width of a human hair. These amazingly sensitive detectors come from amazing technology that has been put into these detectors. LIGO detectors use the purest and most stable lasers in the world. They also comprise the 3rd largest vacuum system in the world. The first being the Large Hadron Collider in CERN, the second being a vacuum test facility run by NASA. LIGO also uses premier optical coating technology, and the mirrors that LIGO has procured have been polished down to within 1 nanometer of what the design specifies. The mirrors for LIGO are hung using a quadruple pendulum suspension. And this is what we use to filter out ground motion. So this is why the LIGO detectors end up being able to not be as sensitive to the ground motion as they would be otherwise.
Do they self-realign when that happens?
There is an active alignment process that happens. It's a whole pipeline of things that happen. You have to align first one mirror and then another mirror and then the whole thing together. But in a quadruple pendulum suspension, you have the final mirror that the laser is bouncing off of at the very bottom. That's hung from another mass, which is hung from another mass, which is hung from another mass. So 4 stages of filtering that ground motion goes through, and the final mirrors are held very still because of all of this filtering. Yes.
When someone in the group asks a question, please repeat it so that it's not on the Zoomers.
Yes.
So they're not hearing us talk.
Okay. Yes.
What wavelength is the laser?
The laser, the input wavelength, I think, is 832 nanometers, but that gets the wavelength gets doubled, and what's actually circulating in the detector is 1064 nanometers. Sorry, the question was, what wavelength of laser light does LIGO use? So 1064 nanometers is what's in the detector. One other way that noise is filtered in LIGO is using glass threads to suspend the final stage of the mirrors. Rather than using steel cables or steel threads that are used everywhere else, indicated by blue, the final stage is hung by glass threads that have been fused to the mirrors. And that helps to filter out the noise that you can get just from the connections of these wires to the mirrors themselves.
Tell us everything you got.
This is a picture of what the suspensions looked like when they were actually installed within the detector. And there's many more technologies that have gone into LIGO that I can't name right now, but it blows my mind thinking about it. Let me focus for a little bit on the noise sources that are limiting the sensitivity of LIGO. So this graph on the right shows the sensitivity of LIGO in terms of strain. So that's a dimensionless quantity. Essentially, it's the distance that LIGO is able to measure changes divided by the arm length of the detector. And this is plotted versus frequency. And you get different sensitivity for different frequency gravitational waves. You look at the dominant noise source in the detector over most of the frequency range. You see this purple curve, which is from quantum noise. And the two areas that contribute to quantum noise from the laser light itself. At high frequency end, you have quantum noise coming from shot noise, which is just counting photons that are coming out of the detector. And the counting statistics of just few photons are the noise source that you predominantly see at high frequencies. You end up having radiation pressure being the dominant noise source. And this is where photons are bouncing off of the mirrors and causing the mirrors to vibrate in an uncontrolled way. So you end up having these two competing effects due to the laser light. If you increase the laser light in the detector, you can reduce or make the detector more sensitive at high frequencies, but increased laser light in the detector will cause an increase in the radiation pressure or the light bouncing off of the mirrors. So you end up having to balance this laser power in order to get the most sensitive detector in the range that you want. These detectors themselves are not like telescopes that you're used to. A telescope, you can point at a particular spot in the sky and see what is there. These detectors work more like antenna, where they're sensitive to all directions. If there's a gravitational wave coming in from basically anywhere on the sky, the detector would be sensitive to it. And this figure is showing how sensitive the detectors are to different directions. If there's a gravitational wave coming from above the detector down, these red lines here indicate where the arms of the detector would be. So if you have a gravitational wave source coming down from above the detector, that's where the detector is most sensitive. And the detector is actually not sensitive at all to directions that are aligned between the detector arms. But with a single detector, you're seeing the whole sky, and you can't really point a telescope using the signals from a single detector. Let me talk now about the global network of gravitational wave detectors. There are gravitational wave detectors in LIGO. There's two detectors. There's the LIGO Hanford detector and the LIGO Livingston detector. The Hanford detectors in Hanford, Washington, and the Livingston detectors in Livingston, Louisiana. These detectors are essentially designed. In addition, there are some other detectors around the world. There's the Virgo detector in Pisa, Italy. There's the GW detector in Hanover, Germany. Also the Kagra detector in Japan. These are all detectors that are currently operating. Well, they're operational. They have operated. Right now, they're being upgraded before they do more science runs. In addition, there's a LIGO detector that's being planned in India. And this is where they've taken some of the instrumentation from a second detector that we used to have in LIGO Hanford and shipped it to LIGO India. And they're building the facility there now. And hopefully in a few years, it will be up and running to contribute to the network of detectors.
What's the purpose of that network?
I'll talk about that right now. So the reason you want a global network of gravitational wave detectors is to increase the sensitivity and to increase the sky coverage. If you have more detectors that are able to detect a particular gravitational wave source or event, then you can say more confidently, this is actually a gravitational wave source. Less likely to happen due to random ways, or if the detectors are in separate places around the world, it's less likely to happen due to some other terrestrial process.
Earthquakes must quite happen.
Yes, earthquakes would mess up the detectors. It'll knock them out of alignment. But the speed that earthquakes travel in the Earth is a lot slower than the gravitational waves.
What about the crust moving, the different crusts?
Motion of just tectonic plates. The question is, what about tectonic plate motion? That's not something that that LIGO would be sensitive to. It's more the large earthquakes that would cause the mirrors to shake that would be an issue. The mirrors, I don't know off the top of my head. They're roughly
as to what so what do I have to do to get a recommendation from you? The walkers mentioned it is.
Sorry, the question was, how big are the mirrors? They're about 18 inches and they're accurate, polished down to about 1 nanometer. Yes.
How do they determine where the proper site?
How did they determine where to put the LIGO detectors? There was lots of studies that were done and multiple places were proposed. Hanford Washington detector is at the Hanford nuclear site, and the Livingston, Louisiana detector. That one actually, there's a lot of politics that were going on behind that, not just for the science community, but politicians as well. They would look for, scientifically, they'd look for ground motion that was fairly stable, and they also needed very large spaces that were away from people. So they, that's why these particular places were chosen. The thing that having a global network of gravitational wave detectors gets you is when these detectors are not aligned with each other, then you can combine the signals from the gravitational wave detectors and have better sky coverage. This plot shows in red more sensitive regions where the gravitational wave detectors are sensitive to gravitational waves. The blue regions show where the network of detectors is less sensitive. If you add additional detectors to this, these blue regions will turn more and more red. And that helps you not miss gravitational waves that could be coming from certain parts of the sky. In addition, having a global network lets you operate a little more like a telescope. The reason I say this is because once you have a global network of gravitational wave detectors, you can do better and better source localization. So that's where you're able to say, this particular patch of the sky is where we think a gravitational wave came from. And as you have more detectors, as you have detectors that are farther apart, this plot here is showing gravitational wave detectors. Here's the Hanford detector. Here's the Livingston detector. This is a map of the Earth. This is the Virgo detector and the detector in India. And these numbers are showing how long it takes a gravitational wave signal to travel from one detector to the other detector in milliseconds. So between Hanford and Livingston, it takes 10 milliseconds for a gravitational wave to travel that distance. As you have more and more detectors in your network, you have larger and larger distances between the detectors, and that gets you better accuracy for saying where a particular gravitational wave source came from. So these plots show that. The blue circles in each of these plots indicate the error that you have for source localization, or being able to tell where the gravitational wave came from as a function of sky position. And then the 4 different panels are different combinations of detectors. This is the worst combination of detectors, which is where you have 2 detectors at the Hanford location, 1 detector at the Livingston location, and then 1 detector at Virgo. The best combination of detectors is this bottom right one, where you would have a proposed detector in Australia. This is when there were competing designs, whether there should be a LIGO India or whether it should be a LIGO Australia detector. it turned out that LIGO India won, but this is what it would have looked like if there was a detector in Australia. This bottom one includes an Australian detector, a detector in Hanford, Washington, a detector in Japan, detector in Livingston, Louisiana, and then the Virgo detector as well. Yes?
Yeah, given our current level of technology and the number of detectors and the number of events that have been confirmed by one or more of these detectors, do we have any idea, either observationally or computer models that say, you know, how many were missing, what percentage?
So the question is, given a certain network of gravitational wave detectors, do we have an idea of how many gravitational wave detections were missing? And that's hard to say because sometimes the detectors go offline and there are different spots in the sky that it's harder to detect the gravitational waves from. All we can really say is these are the sources that we see. And as the detectors get more and more sensitive, we're able to see further and further out into the universe. Now let's talk a little bit about the gravitational wave sources and the detections that LIGO and Virgo and Kagra have made. LIGO was designed to see a certain set of gravitational wave sources. The main source that LIGO was designed to see were sources from inspiraling compact objects. This is where you have a black hole and a neutron star, or two black holes or two neutron stars orbiting each other and emitting gravitational waves. As these objects orbit each other and emit gravitational waves, they lose energy and they get closer and closer together. As they get closer and closer together, they orbit each other faster and then eventually merge. And the final object will vibrate and ring down until it's stationary. That's what this plot on the right is showing. You have two objects that are orbiting each other, getting closer and closer together, merging, and then ringing down. And this is what the gravitational wave signal would look like from an event like that, where the gravitational wave signal is lower frequency, lower amplitude at first, then it becomes higher and higher frequency and higher amplitude until the objects merge, and then you just have a ringing tone that eventually fades away. LIGO was also designed to see gravitational waves from supernova, galactic supernova. We haven't had any while LIGO has been operating, so it hasn't detected any of those. And it's also sensitive to gravitational wave signals from spinning neutron stars that would be pulsars if they're emitting a radio pulse as well. A pulsar would actually only be emitting gravitational waves, though, if there's a small bump or a small mountain on the pulsar itself. And as that bump is moving around with the pulsar spinning, that's the part of the pulsar that would be generating the gravitational waves. And LIGO hasn't detected those types of signals. In addition, LIGO would be sensitive to a gravitational wave background. This could come from either the inflationary period of the universe or from having a large collection of gravitational wave signals that are all happening at the same time, such that it can't distinguish any one of them. It would just be a gravitational wave background that it was able to detect. So what signals has LIGO actually seen? This plot shows the masses of binary objects that LIGO has detected over the first, second, and third observation runs that it has done. The y-axis of this plot shows the mass of the individual objects and then also the final object. And the color indicates what type of objects these were. Blue corresponds to black holes. Orange corresponds to neutron stars. And those are the events that LIGO has detected. We can compare these masses to the masses of black holes and neutron stars that have been detected in our galaxy by electromagnetic observations. And that's what you see in red for the electromagnetically observed black holes, and yellow for the electromagnetically observed neutron stars. And the types of signals that LIGO has seen include signals from binary black holes, binary neutron stars, and also combinations of one neutron star and one black hole. Let me focus on a few of what I consider the extraordinary detections that LIGO has made. The first one is GW 150914. This is a gravitational wave event. That's what the GW stands for. 15 corresponds to the year that this was detected, 2015. 09 is September, and 14 is the 14th. This is a very special day. And for me, it was very special because it was the day after my son was born. This was actually a very unexpected gravitational wave signal. The LIGO detectors were not officially doing an observation run. One was scheduled to happen a few days later, but they were operating in the same mode that they would be for the observation run. While they were operating, they saw this signal come in, and there was a lot of confusion that happened after that. They had to check to make sure that nobody accidentally put this gravitational wave signal in the detectors through some other way. But it turns out it was a real event, and the rest is history.
Drew?
Yes.
And there's a question that came in from Rich. It asked, how many events are there on the graveyard graphic? I think that was the previous slide.
Yes.
This one.
Let me go back. So on this graphic, there's about 90 gravitational wave detections on this graph. So the question was, how many gravitational waves have been detected by LIGO and are shown on this graph? And this includes about 90. So another reason why this gravitational wave signal was unexpected was because it came from the merger of a 36 solar mass black hole and a 29 solar mass black hole. These objects were very large, and these masses were unexpected for stellar mass black holes. For a single star, we had not observed black holes this large to come from just normal stellar evolution. This gravitational wave detection also provided further confirmation that general relativity was correct, because it was the first direct detection of gravitational waves that were predicted by general relativity. And this led to the 2017 Nobel Prize in Physics for Kip Thorne and Ray Weiss and Barry Barish. The plot on the right here shows what the signal was in the Hanford, Washington detector, and also what the signal was in the Livingston, Louisiana detector. The middle panel shows what just the reconstructed signal was that LIGO estimated to be detected. And if you remove that signal from the data that was collected, you end up with this bottom plot that shows essentially just noise is left in the data. This signal matches very well to what we would get from numerical relativity. And the final bottom panel shows time on the x-axis and frequency on the y-axis, spectrograms. So this is these are common plots that that you look at in gravitational wave data analysis. What you see in this plot is the signal starting out at low frequencies, coming up to high frequencies, and then disappearing. And that's the type of signal that that you'd expect from a binary black hole. The next gravitational wave event I'd like to focus on is GW 170817. So this occurred in 2017 on August 17th. This was the first gravitational wave signal that LIGO detected from a binary neutron star system. And it's also the first gravitational wave signal that was detected that had an optical counterpart, that had an electromagnetic counterpart. Just 1.5 seconds after the gravitational wave signal came through the LIGO detectors, the Fermi gamma ray telescope that's orbiting the Earth also detected a GRB, or a gamma ray burst. This is not a coincidence that Fermi saw this gamma ray burst. And if you look at the sky location where Fermi says this gamma ray burst came from, it's coincident with the sky location that the LIGO detectors say the gravitational wave event came from. A few hours after the gravitational wave event came through, and the scientists saw that there was also a coincident GRB with this event, they sent out an alert to the astronomical community saying, you should look in this region of the sky to see if there's any counterparts. And less than 11 hours later, the SWOPE telescope found an optical counterpart. That's what these two plots show here. On the bottom plot, you see what this region of the sky looked like roughly 20 days before the event. And then almost 11 hours after the gravitational wave event, there's this new dot that SWOPE saw. So this is the optical counterpart to the gravitational wave signal that LIGO found from the binary neutron star system. Further follow-up of this event showed that the spectra corresponded to a kilonova event. And by estimating looking at the spectra, you can see what types of elements were detected in this, or were produced in this event. And what they observed was lots and lots of precious metals, things like gold and platinum. And if you estimate how much gold and platinum would be produced by these events, by binary neutron star merger events, it's enough to provide almost all of the gold and precious metals that we have here on Earth. That means that the gold and the platinum and all the precious metals we have here are most likely produced from binary neutron star mergers that happened way before the Earth was created.
You know, that inspires a question that may sound stupid, but would it be reasonable to assume that our Earth contains all the elements that you will find in the rest of the universe, and not any other elements would exist out there because of what we've seen so far?
The question is it reasonable to assume whether our Earth contains all of the elements that exist in the universe and there's no others that exist outside of Earth?
Based on what we've seen.
Based on what we've seen. I don't know if you compare the ratios of all the elements that we have here on Earth to what channels that would produce those in the universe. I don't know whether they all align with what is known, but the precious metals line up with binary neutron star events.
And going back many years, but I seem to remember that we postulated the existence of elements and then found them based on a pyramid style chart of relationships. This is going back to 1960.
I don't know the answer to that.
Okay.
Some other interesting events that LIGO has detected are events like GW 190425 and GW 200115. These are other gravitational wave events that came from neutron star mergers, either with a black hole or with another neutron star. And if you look at all of the gravitational wave signals that were associated with neutron star mergers, and look at the estimated masses for those neutron stars, you end up with a particular mass distribution for neutron stars. And you can compare that to what we observe through electromagnetic observations of binary neutron stars. and you see a much broader distribution. This means that that the galactic binary neutron star population that we see in pulsars has a slightly different formation channel than the formation channel that is causing gravitational waves, that's leading to gravitational waves from neutron stars. This has led to research into this area where researchers are looking at whether there's models for stellar evolution that can provide these types of signals. And recently, there was a paper talking about how binary systems could do this, where you have one massive star that goes supernova first and produces a neutron star. The other one that's a little bit lighter takes longer. When it expands, it can either go into one of three channels, a channel where you have a core star that is feeding the neutron star and spinning it up, making it into essentially what a pulsar is. And this is what would match the galactic binary neutron stars that we have seen with pulsars. Or you could have slightly heavier cores. As you have a heavier core, you end up with a smaller object that's less likely to spill over onto the nearby pulsar or onto the nearby neutron star. So you would end up with a binary neutron star where you did not have one of the objects looking like a pulsar. And these two channels are could be what is happening to produce this difference in the mass distribution for binary neutron stars that we see with pulsars versus the binary neutron star signals that we see with LIGO. Let's talk about what LIGO could do going forward. One of the things that that LIGO is able to contribute to is measuring the Hubble constant. LIGO would be able to provide an independent measurement of the Hubble constant compared to things like type 1a supernova or estimating the Hubble constant from the cosmic microwave background. Here, this plot shows a probability distribution. So there's probability on the y-axis versus different values of the Hubble constant. And given the gravitational wave GW 170817, that's the first binary neutron star observation with the electromagnetic counterpart. From that measurement, you're able to get a certain probability distribution for what you estimate the Hubble constant to be. And it overlaps with the two estimates from the cosmic microwave background and from the type 1a supernova. And as what LIGO should do in the future is as it detects more and more of these binary neutron star signals where we have electromagnetic counterparts, this distribution will get narrower and narrower and help us determine whether there's one of these values that's correct. Does it agree more with the cosmic microwave background value, or does it agree more with the type 1a supernova value? Is there a question?
Yeah. Is there any pattern or quasi-predictable period between detected gravitational waves to date? Or are they somewhat random?
Is there any pattern to gravitational waves detected to date, or are they somewhat random? That's actually something that researchers have been studying. If you have a pattern between gravitational wave events that would look like the same event was repeated, or a slightly higher mass event came after a smaller mass event, that could indicate a gravitational wave event that had actually been gravitationally lensed by a galaxy between Earth and the origin of that gravitational wave.
Thank you very much.
Like that has been detected. And the ones that have come in are mostly random. One of the other things that LIGO could say in the future is provide evidence for what the origin of the gravitational wave source population is. Are these gravitational wave sources coming from isolated binary evolution, like you'd get from two stars that formed together, and then one of them turned into a neutron star or black hole, and then the other one turned into a neutron star or black hole? Or are these events coming from dynamic formation, where you have a dense stellar environment, like a globular cluster or the core of a galaxy, where black holes or neutron stars are passing by each other and then getting captured and forming a system that then turns into a gravitational wave event, or then emits a gravitational wave event. Ways that you could tell between these two types of formation channels are looking at the spin distributions for black holes, looking at how the spins of the individual objects are oriented compared to the angular momentum of the objects orbiting each other. If those spin distributions seem to be random compared to the orbital angular momentum, that indicates that these objects were more likely formed through the dynamic channel. If you have spins that are mostly aligned with the orbital angular momentum, that indicates that these are most likely due to isolated binary evolution. Another way you could tell something similar is by looking at the residual eccentricity of the objects that are orbiting and causing these gravitational wave signals. The eccentricity is essentially how non-circular these orbits are as the objects are getting closer and closer together. In isolated binary evolution, you'd expect the eccentricity to be almost non-existent. The orbits would be very circular. Whereas in a dynamic formation scenario, you would have events that capture each other and are orbiting each other very eccentrically before they merge. And there's hints that this may be happening with some of the binary black hole events that have been detected. But we need to do more follow-up studies before it can be confirmed. Now let's talk a little bit about the impact of LIGO on astronomy. In addition to LIGO being able to detect gravitational waves, there's other types of detectors that can also detect gravitational waves. And LIGO has really energized the field of gravitational wave astronomy so that these things are going forward with renewed vigor. One way that you can detect gravitational waves is by looking at the cosmic microwave background. Another way is by looking at pulsar blips that are coming in and creating a pulsar timing array to look for gravitational wave signals in a different frequency range. Another way to detect gravitational waves is taking the same type of setup that LIGO has, an interferometer, and sending that into space and having that be just much bigger compared to what LIGO is. All of these types of detectors are sensitive to different frequency ranges and to different types of signals. The cosmic microwave background has actually been analyzed looking for certain modes of the polarization of the CMB. These gravitational wave signals would correspond to femtohertz gravitational wave signals, and they would come from the inflationary period of the universe. BICEP and Planck have been working together in order to set constraints on gravitational wave signals from these models. And so far, they haven't detected anything yet, but they have been able to rule out certain inflationary models using the data they've collected. Pulsar timing arrays are also operating currently. These operate by taking millisecond pulsars and using them as clocks. You see here in this figure, there's these white dots are pulsars that are pointing towards the Earth, so we're able to detect the pulsar signals from the radio jets. If you time the signals coming from these pulsars, you can look for spatial correlations between deviations from the expected arrival times. And using those spatial correlations, you can tell whether there's gravitational waves at certain amplitudes that the Earth and these pulsars are sitting in. These types of gravitational wave signals would come from objects like supermassive black hole binaries. So these are black holes that are at the center of galaxies. As galaxies merge, the black holes at the center of those galaxies will eventually merge as well. And orbiting each other, they'll produce a similar signal to what LIGO has seen, but at a much stronger amplitude and much lower frequency range. Recently, the International Pulsar Timing Array, IPTA, has released some data showing strong evidence for a low frequency gravitational wave signal. This isn't yet to the level where they want to claim detection of a gravitational wave signal, but it's consistent with what you would expect from a gravitational wave background formed by many overlapping gravitational wave signals due to supermassive black hole mergers. Finally, there's also LISA, the Laser Interferometer Space Antenna. This is something that has, research has continued into the technology that would be needed by LISA. And a few years ago, there was a LISA Pathfinder mission that, that went up into space to demonstrate the technology needed for LISA. And what they found was already at the level that they had produced the technology, you would be able to detect the gravitational wave signals that LISA is expecting to detect. They didn't detect gravitational waves, but the technology is ready to build LISA so that you can launch it and then operate it. One thing I forgot to say is that LISA is similar to LIGO. It's a laser interferometer observatory, but instead of being on Earth, it's out in space, and it's a constellation of 3 spacecraft that are orbiting behind the Earth and tumbling with respect to each other. Thank you for listening to my presentation. I hope you learned about LIGO and enjoyed learning how it contributes to gravitational wave astronomy and astronomy in general. Yes.
I have one question. Since LIGO detects basically the difference in distance from the photons hitting mirrors, et cetera, I assume that the physical properties of LIGO are changing. If that's the case, then anything the gravity wave hits or affects also changes, which includes every human on the planet in a minuscule way. Mm-hmm. So we grow and shrink or squish and whatever with each event.
Yes, we would have similar effects as what LIGO is sensitive to, but it's not something that is causing us to grow and grow and grow and grow. These are oscillating. So you get a little bit bigger, a little bit smaller, a little bit taller, a little bit shorter. Yes.
Would LIGO detect coronal mass ejections?
I don't know. I don't know.
Because that's a lot of mass close by.
The question was, can LIGO detect coronal mass ejections? I don't know. I suspect not. I don't think it's enough mass to accelerating fast enough to produce a gravitational wave signal that LIGO would be sensitive to. These objects are black holes, the most massive objects in the universe. And they're traveling at near the speed of light when they're finally merging with each other.
Yeah,
so that's true. I don't think so, but I don't know.
There's a question from the audience. Can gravitational waves intersect or collide with each other? Assuming they can, what is the net effect, if any, in the locales of such a wave intersection?
So can gravitational waves collide and intersect with each other? And if so, what are the effects? It'd be similar to what you have when waves on the ocean collide or intersect with each other. Basically, they pass through each other for the most part. One thing that is interesting about if you're able to focus gravitational waves, the very first time that numerical relativity was able to simulate black holes was by focusing gravitational waves into a single spot that then formed a black hole in the simulation. So the black holes, the gravitational waves can interact with each other and form like a black hole, which would then persist. But for the most part, they're just going to pass through each other.
Okay, if there's no more questions, then thank you very much.
I'll shut that off.